Today we discuss section 2.4 coordinates. In this session, we discuss the importance of coordinates and the definition of the coordinates. Before I give the definition of the coordinates, let's see an example. If we start with V is the vector space of all real polynomials of degree at most 3. Okay, clearly this V is a vector space over R. R is the corresponding field. Then the elements of V is nothing but A0 plus A1x plus A2x square plus A3x cube, where each AI are elements of real numbers. This is the vector space of all polynomial of degree at most 3. Now consider a subset of V as 1x x square x cube. This is a subset of V, and this subset has the following properties. The first property is whenever C1 plus C2 x plus C3 x square plus C4 x raised to 3 equal to 0 implies C1 equal to C2 equal to C3 equal to C4 is equal to 0. That means the set V is linearly independent. Then we can say that any element of V, any polynomial P of x belongs to V is a linear combination of elements of B. This shows that this B is a basis for V. Okay, so if you consider an element x belongs to V, then x takes the form 0 plus 1x plus 0x square plus 0x cube. Okay, this will give a straight line passing through origin. Okay, so this is our x. If we choose another vector x square belongs to V, you can get the corresponding expression as 0 plus 0x plus 1x square plus 0x cube. So that is a parabola. These are all polynomials. So this is a parabola. Again, if we set x cube as an element of V, you can write it as x cube is equal to 0 plus 0x plus 0x square plus 1 times x cube. Okay, so that will be a graph like this. So when you choose this A0, A1 or AI, you can get different polynomials in V. Okay, suppose we need to send a polynomial to we have a sender here and we have a receiver. Suppose we need to send a polynomial over here. Okay, in order to send the P of x. So in order to identify such polynomial, we need to bother about the exact expression of this. We need to consider only the coefficients. The coefficient will give the in order to decode the polynomial, it is enough to get these coefficients a0, a1, a2, etc. a0. So if this is the polynomial, we represent this polynomial as 0, 1, 0, 0. Okay, only this much information is enough to identify such x. Okay, similarly, in order to identify this x square, we need to collect the coefficient of those polynomials 0, 0, 1, 0. Okay, similarly, in order to collect this, we need to consider 0, 0, 0, 1. Okay, so these are called, actually these are the coefficients corresponding to the basis element. Okay. So this coefficients are called coordinates. Okay, in order to send the whole information of this polynomial, we need not bother about the other things. We need to get only these much coefficients or elements of f. Okay, or in this case these are the elements of r. So these coordinates is called the coordinate of the vector x with respect to the basis b. So now we represent the coordinate of x with respect to b is equal to 0 1 0 0. We represent it as a matrices. Okay, it is a column matrix. So we can say that each element alpha belongs to b. If we set a basis, then you can get coordinates. Okay, so this is x1 x2, these are elements of corresponding field. Okay, so when you write this basis element as 1 instead of x, if we put x square here, then x cube, then this will change. Okay, in order to represent x, we need to write this 0 0 1 0. Okay, then only we can say that with respect to these quantities, the corresponding coordinate is 0 0 1 0. Okay, so the ordering of these elements are very important. Well, such in this case, this basis is called ordered basis. Okay. Ordered basis is a basis in which the ordering of the element is important. So even though the ordering are concerned, we represent that as elements in a set. Okay, x square, x cube. Okay, if this order is concerned, this is what we call an ordered basis. Okay, yeah, if whenever we consider the ordering, then the corresponding basis is called ordered base. Okay, when you consider these coordinates, so we need to consider only the ordered basis. Okay, this is the advantages of coordinates. I'll conclude. That is, whenever a sender has to send a polynomial to, or some vector to another receiver, we need to set the ordered basis 1 x x square x cube in both sides. Okay, first we share this ordered basis. Actually, this will be represented by a set, and we will share sender and receiver share this basis vectors first. Then, in order to send a polynomial, we need to send only the coefficients. This is the idea of coordinates. Okay, we need to send all these coefficients. Okay, so this will give the corresponding polynomial what the sender sent to this receiver. Okay. Now let's see the formal definition of ordered basis. If V is a finite dimensional vector space, an ordered basis for V is a finite sequence of vectors, still that is represented by some alpha 1, alpha 2, etc. alpha n using the set notation, which is linearly independent and spans V. Okay, even though the sequences, even though the basis elements are considered as sequence, we write it as in a set notation. So this is the notation for an ordered basis. Okay. Now we take an x from an alpha from V. If you take an alpha, a vector from V, then you can easily write this alpha as a linear combination of these basis vectors. Then you can write it as x1 alpha 1 plus x2 alpha 2 plus etc. Xn alpha n. Over here the tuple or the matrix x1 x2 matrix of coordinate coefficients is called, this is coordinates of alpha with respect to the basis b. Okay, whenever you write like this, the notation in summation notation we can write it as sigma I equal to 1 to n xi alpha I. This is the notation for alpha. Now, whenever we write the alpha as another linear combination of these ordered pairs, these ordered vectors, we can write say x1 prime alpha 1, x2 prime alpha 2, etc. xn prime alpha n. So this the same alpha is a linear combination of another linear combination of alpha 1, alpha 2, etc. alpha n. So this is nothing but in summation notation, this is I equal to 1 to n xi prime alpha I. Then by subtracting, you can get 0 is equal to summation I equal to 1 to n xi minus xi prime times alpha 1. Okay, so this shows that x1 minus x1 prime alpha 1 plus etc. xn minus xn prime alpha n. Since this alpha 1, alpha 2, alpha n are linearly independent, whenever this linear combination is 0, then each coefficient is 0. So we can get xi is equal to xi prime for all I. This shows that these two expressions are, or these two coordinates, in this case the coordinate is x1 prime etc. xn prime. Okay, that is the coordinates of alpha with respect to the same b. Okay, so when you fix this ordered basis, these two coordinates are exactly the same. That is what we have proved here. If alpha can be written as two linear combinations of elements of the basis b, where b is an ordered basis, then those coefficients or coordinates are the same. This shows that if we fix an ordered basis, then coordinate of any element with respect to that ordered basis is unique. Okay, this is the basic idea of the coordinates, because while you identify alpha, we collect these coefficients x1 etc. xn. This is enough to represent this alpha. This is the idea behind here. So for any alpha belongs to be, the coordinates are unique. There is a unique expression for alpha as a linear combination of elements of ordered basis beta.